Consider the series from 1 to infinity of 1 over n plus 2 squared. So will this series converge or diverge? So in this video, we're going to use the integral test to find the answer. So let's say the sequence a sub n can be described as a function of n. In order for the integral test to work, the function must be positive, it has to be continuous, and it has to be decreasing. Now, all of this must be true when x is equal to or greater than 1. So it has to be true on the interval from 1 to infinity. So if these three conditions are satisfied, then we can use the integral test. So here's the basic idea behind the integral test. If you take the integral from 1 to infinity of f of x dx, and let's say you get a finite number, which we'll call n, then the integral converges, which means that the series will also be convergent. Now, let's say if you take the integral, but you don't get a finite number. Let's say if you get infinity or negative infinity, then the integral diverges. And so if the integral diverges, according to the integral test, the series must also diverge. And so that's the basic idea behind the integral test. So now let's finish working on this problem. So let's write the corresponding function f of x, which is 1 over x plus 2 squared. So is this function positive? What would you say? Well, looking at x plus 2 squared, regardless of what value that we plug in, it's always positive except when x is negative 2, because we're going to have a vertical asymptote there. So for the most part, this is a positive function. Now, is it continuous? Because we have a vertical asymptote at negative 2, that's basically an infinite discontinuity at that point. So it's not continuous everywhere. So does it satisfy this condition? Now, remember, it only has to be continuous on this interval and not everywhere. So is this discontinuity, is it in the interval? Negative 2 is not in the interval. So from 1 to infinity, it's continuous everywhere in this interval. Therefore, the second criteria has been satisfied. Now let's focus on the third point. Is the function always decreasing? The way we can determine that is by taking the first derivative, or using the first derivative test. If the first derivative is negative, then the function is decreasing. So we need to show that the first derivative is negative on this interval. So let's go ahead and find the first derivative. So let's begin by rewriting it as x plus 2 raised to minus 2. And now let's take the first derivative of that function. So using the power rule, it's going to be negative 2 times x plus 2, and then negative 2 minus 1 is negative 3. And then you need to multiply by the derivative of the nested function, which is 1. So rewriting this is going to be negative 2 over x plus 2 to the third power. So looking at f prime of x, what can you tell me about the first derivative, about the sign of the first derivative? Well, let's make a sign chart. So we still have a point of discontinuity at negative 2. And at that point, it can change sign. So let's say if we plugged in negative 3. Negative 3 plus 2 is negative, and it's raised to the third power, so it's going to stay negative. And the negative divided by negative will give us a positive value. Now, if we plug in a number that's greater than negative 2, like 0, 0 plus 2 is positive, so a negative number divided by a positive number will give us a negative result. So from negative 2 to infinity, the first derivative is negative, which means that the function f of x is decreasing. So if it's decreasing from -2 to infinity, it's also decreasing on the interval from 1 to infinity. And so that's one way you can show that the function is decreasing on this interval. It's by taking the first derivative and making sure that the first derivative is negative on that interval. So once you show that the three conditions are satisfied, you can now use the integral test. So let's evaluate the integral from 1 to infinity of the function f of x dx. So this is an improper integral. So we need to set it up this way. Let's use b, the limit as b approaches infinity from 1 to b, and then f of x is 1 over x plus 2 dx. So at this point, I can get rid of this stuff. We don't need that anymore. So let's focus on this integral. And we can come back to this expression. So we need to do U-Substitution. So let's make u equal to x plus 2, and so du is equal to dx. So we have the integral from 1 over u, and then actually it's 1 over u squared times du. So we can write it as u to -2, and then using the power rule for integration, -2 plus 1 is -1. And so this is going to be -1 over u, and then replacing, we really don't need the c here, replacing u with x plus 2, it's going to be -1 over x plus 2. So this is going to be equal to the limit as b approaches infinity, and then this integral is going to be -1 over x plus 2 evaluated from 1 to b. So we're going to have the limit as b approaches infinity, and then we're going to plug in b into this expression. So it's going to be -1 over b plus 2, and then minus, now we need to plug in 1, so it's going to be -1 over 1 plus 2, which is 3. Now, the limit as b approaches infinity for -1 over b plus 2, that's going to go to 0. If it was 1 over b, that will go to 0 as well. So -1 over b over 2, -1 over b plus 2, that's also going to go to 0. And then we have minus -1/3, so this is going to be plus 1/3. So because we get a finite value, we could say that the integral converges to 1 over 3. So if the integral converges, then according to the integral test, the series must also converge. And so that's it for this problem. Now let's try another example. So let's say we have a series with the sequence 2n over 3n squared plus 4. So go ahead and use the integral test to determine if the series will converge or diverge. So let's begin by writing the corresponding function. So f of x is going to be 2x divided by 3x squared plus 4. Now, there are no points of discontinuity for this function. So the function is definitely continuous. Is it positive? Well, when x is greater than or equal to 1, it will always be positive. 2x will be positive when x is a positive number. It will only be negative when x is less than 0. And since x is equal to or greater than 1, 2x will be positive. And 3x squared plus 4, that's going to be positive as well, because x squared is always positive. So we have a positive function. Now, is it a decreasing function? So we need to find the first derivative in order to determine that. Now we're going to have to use the quotient rule to get the answer. So if you recall, the derivative of u over v is going to be vu prime minus uv prime over v squared. So u, in this example, is 2x, v is 3x squared plus 4. So f prime of x is going to be v, which is this, times u prime, so that's 2, minus u, and then times v prime, which is 6x, all divided by v squared, and that's 3x squared plus 4 squared. So let's begin by distributing the 2. So first I'm just going to have to get rid of some stuff. And so this is going to be 6x squared plus 8, and then 2x times 6x, that's 12x. And then this should be 12x squared. 6x squared minus 12x squared, that's going to be negative 6x squared. Now let's see when this expression is less than or equal to 0. We want to determine when it's negative. So let's identify the critical points. If we set the denominator equal to 0, we're not going to get any values for x. 3x squared plus 4 will never be 0. Now we can set the numerator equal to 0. If we add 6x squared to both sides, we'll get this, and then we'll divide by 6. So 8 over 6 is equal to x squared, and then we can reduce that to 4 over 3. So taking the square root of both sides, we're going to get plus or minus 2 over the square root of 3. Now let's create a sign chart. Now 2 divided by the square root of 3 as a decimal, that's 1.155 approximately. So we need it to be negative from 1 to infinity. So 1 is somewhere in this region. Just keep that in mind. Now let's say if we plug in 2. 8 minus 6 times 2 squared, is that going to be positive or negative? If you plug in 2, this will be negative, but on the bottom, that's always going to be positive. So this is negative in this region. Now if we plug in 0, 8 minus 6 times 0 squared, that's 8. And the bottom will still be positive. So therefore, this will be positive in this region. And then if we plug in, let's say, negative 4, the numerator will be negative, and the bottom will be positive, so this is going to be negative. So looking at the sign chart, we know the function is decreasing from 2 over square root 3 to infinity. But it's not decreasing from 1 to infinity, so we can't use the integral test in that region. We could, however, use the integral test from 2 to infinity, because it's continuous there. And we can't use this number in a sequence because it's not an integer. For the sequence a sub n, you can only use integers. So let's determine the integral from 2 to infinity, and let's see if it converges or diverges. So f of x is 2x over 3x squared plus 4. So let's use U-Substitution. We're going to make u equal to 3x squared plus 4, and so du is going to be 6x dx. And so dx is du over 6x. So this is going to be u on the bottom, and then replace dx with du over 6x. So 2x over 6x, that's going to be 1/3. So this is 1/3 times the integral of 1 du, which is going to be 1/3 ln u, and then that's going to be 1/3 ln 3x squared plus 4. So now we're going to make this integral equal to the limit as b approaches infinity for the integral 2 to b 2x over 3x squared plus 4 dx. And so that's going to be the limit as b approaches infinity. And so we're going to get 1/3 natural log 3x squared plus 4 evaluated from 2 to b. So we no longer need the absolute value expression because 3x squared plus 4 is always positive. So we now have the limit as b approaches infinity, and then this is 1/3 natural log 3b squared plus 4, and then minus. Now let's plug in 2. So 1/3 ln 2 squared is 4 times 3, that's 12 plus 4, that's 16. Now as b goes into infinity, what happens to ln 3b squared plus 4? Infinity squared is infinity. If you multiply that by 3 then add 4, you're still going to get infinity. And the natural log of infinity is still infinity. So this entire expression goes to infinity. So infinity minus some finite number is still going to be infinity. Therefore, since the integral from 2 to infinity of f of x dx, because it equals infinity, it doesn't equal a finite number, we could say that the integral diverges. And if the integral diverges, then the series from 2 to infinity of a sub n, which was 2n over 3n squared plus 4, this will also diverge. Now, if this series diverges, what about the original series? Let's say from 1 to infinity. The only difference between these two series is that this one has an extra term, the a sub 1 term. So if we add the second term to an infinite number of terms and we get a divergent sum, then if we add the first term to basically a divergent sum of infinity, the first term plus infinity will still be equal to infinity. So therefore, this series must also diverge. And so that's the answer for this problem. We have a divergent series. Now let's talk about the harmonic series from 1 to infinity. If we list out the terms, it's going to be 1 plus 1/2 plus 1 over 3 plus 1 over 4, and so forth. Now we know that the harmonic series is the divergent series, but use the integral test to show that it's divergent. So let's begin with the corresponding function 1 over x. Now let's draw a graph of it. Now the graph looks like this, and it has a vertical asymptote at x equals 0. But let's focus from 1 to infinity. So from 1 to infinity, the function is positive because it's above the x-axis. It's also continuous from 1 to infinity. There's no infinite discontinuities, no holes, no jump discontinuities in that region. And finally, you can see that it's decreasing from 1 to infinity. It's going down. So all three conditions are met for this particular function. So we could use the integral test. So let's integrate it from 1 to infinity, 1 over x dx. So this is going to equal the limit as b approaches infinity, integral 1 to b, 1 over x dx. The antiderivative of 1 over x is the natural log of x. And let's evaluate from 1 to b as b goes to infinity. So we're going to have the limit as b goes to infinity, ln b minus ln 1. Now, the natural log of infinity is infinity, and ln1 is 0. So therefore, the integral diverges to infinity, which means that the series also diverges. Now let's talk about this particular series. Let's say it's 2 divided by n squared plus 6n plus 10. So go ahead and use the integral test to see if the series is going to converge or diverge. Now the first thing I would recommend doing is rearranging this expression. So let's focus on n squared plus 6n plus 10. And let's complete the square. So half of 6 is 3, and 3 squared is 9. So instead of writing 10, I'm going to write 9 plus 1, because this is a perfect square trinomial. Two numbers that multiply to 9 but add to 6 is 3. So it's going to be n plus 3 times n plus 3, which we can write it as n plus 3 squared plus 1. So now we have this particular series. So now let's write the corresponding function. So f of x is going to be 2 divided by x plus 3 squared plus 1. So is this function always positive? X plus 3 squared will always be positive, and everything else is positive. So this function is always going to be positive everywhere. Now, is it continuous? There are no points of discontinuity. X plus 3 squared is always positive, and then if you add 1 to it, it will never be 0 on the bottom. So it's continuous everywhere. There are no points of discontinuity. Now, is it a decreasing function? The fact that it's a bottom-heavy function that's always positive indicates that it's a decreasing function. But if you want to, you can go ahead and find the first derivative. If you were to draw a rough sketch of the graph of this function, you'll see that at negative 3, it has its highest value of 2. Negative 3 plus 3, that's 0. And so it becomes 2 over 1. And so that's the maximum value of the function. And then after that point, it follows the x-axis. And so if we focus on a region from 1 to infinity, you could see that it's a decreasing function, it's positive, it's above the x-axis, and it's continuous everywhere from 1 to infinity. So we can use the integral test for that function. Now let's find the integral from 1 to infinity of the corresponding function 2 over x plus 3 squared plus 1. So for this problem, we need to use trig substitution. And if you see an integral with this generic formula or generic expression, this is equal to arctangent of x. So this is going to be equal to something related to arctangent. So what we're going to do is replace x plus 3 with tangent theta. Now, if we differentiate both sides, we're going to get dx is equal to the derivative of tangent, which is secant squared theta times d theta. So let's replace x plus 3 with tangent. So this is going to be tangent squared. And let's replace dx with secant squared theta d theta. One plus tan squared is equal to secant squared. So now we can cancel these two expressions. And so this is going to give us the integral of 2 d theta, which is 2 theta. Now, if x plus 3 is equal to tan theta, theta is arctan of x plus 3. So we're going to have 2 times arctangent x plus 3. Therefore, the integral from 1 to infinity of 2 divided by x plus 3 squared plus 1, that's going to be equal to the limit as b approaches infinity for the integral 1 to b of the same expression. And let's not forget dx. So this is going to equal the limit as b approaches infinity, and then we're going to have 2 times arctangent x plus 3 from 1 to b. And so that's going to be the limit as b approaches infinity, and then it's going to be 2 arctangent b plus 3, and then minus 2 arctangent, and then it's going to be 1 plus 3, which is 4. So infinity plus 3, that's going to be infinity. So what is arctangent of infinity? If you draw a graph of arctangent, it has 2 vertical asymptotes. Not vertical asymptotes, but horizontal asymptotes. One at pi over 2 and the other at negative pi over 2. And the graph looks something like this. So as x approaches positive infinity on the right, the y value will approach pi over 2. So arctangent of infinity is pi over 2. Now, if you put your calculator in radian mode, and if you type in arctangent of 1,000, it will give you 1.57, which is approximately pi over 2. Or if you put it in degree mode and type in arctangent of 1,000, it will give you 89.9, which is close to 90 degrees, which is about pi over 2. So this part, as b goes to infinity, that's going to converge to pi over 2. So this expression, pi over 2 minus 2 arctangent of 4, it has a finite value, which means that the integral converges. And so if the integral is convergent, then the series will also converge. And that's the final answer.